everyone, welcome to Vedantu J English. I am Diksha Kaushal, your chemistry master teacher. So everybody, today we are going to complete hydrocarbons, right? In the last lecture we have done till preparation of alkynes, and today like really important reactions you have in today's lecture, right? So we are going to do properties, physical properties, chemical properties of alkyne, then we will talk about aromatic hydrocarbons. See, aromaticity we have already talked about, but here we will talk about the reactions of aromatic hydrocarbons, right? So some reactions you are very familiar with, but some reactions will be very new for you. So everybody, watch this lecture till the end because that is going to be very beneficial for you. Don't just lose motivation in between, because just watching half lecture is not going to contribute to your preparation. You have to watch the lecture till the end, have that kind of patience, right? Okay, so everybody, Kiru, Pavan, very good Pavan, very good, very happy for you. Bala, Kuti, Vijay, Zozo, and yes, everyone, Manoj, ready for the session. Now what we did in the last class, like before that, let me just remind you that our test series, which is at 999, it is at the discounted price at this point, and this price may end anytime soon. And what you will get here, you will get topic wise test, right? The most repeated topics according to the frequency of the questions, you will get the questions, and then you will get part syllabus and full syllabus test. Around 150 tests will be there, right? And right now is the perfect time to start from the topic wise until you complete your syllabus. Within a month or so you can start with part syllabus and full syllabus tests, right? With the detailed solution it is given to you, and these tests has been made by analyzing previous 20 years of papers, like 20 years PYQs we have analyzed, and we teachers itself have made the test series for you, right? Okay, so right now it is as discounted price. The link is in the description. Go and check that out, guys, right? And the homework, let me tell you, the homework is D, right, that I gave you in the last class, right? And here what exactly they are asking you? They are asking you where you have the formation of acetone and carbon dioxide is eliminated. So that is this, where here double bond O is attached, here double bond O is attached, and hence you will have acetone, and this is nothing but this is C double bond O, this is H, this is H, right? Further oxidation, we will convert this to OH and OH. That will further decompose to H2O and CO2. So answer is going to be ketone CO2 plus H2 also you can write, will be your correct answer here. Okay, so answer will be D is the correct answer for the question that I gave you, right? Okay, so let us start with the physical properties of alkynes. Preparation we have already discussed, guys. So let's talk about the physical properties of the alkynes, right? So starting with this thing here, first thing is C1 to C4 are gases in nature, then they are non-polar, but polarity is still more than alkanes and alkenes, right? Otherwise they are non-polar because the polarity is going to not fully cancel, but polarity is still more than as compared to alkanes and alkenes. Soluble in organic solvents like acetone, alcohol and chloroform, they are soluble in these organic solvents, right? Now this is a very important thing, that this is actually a very important property, right? That is, why are alkynes reactive, right? You will see so many reactions of alkynes, so many chemical properties of alkyne. What is the reason why they are so reactive, right? Let's talk about that. So due to the presence of pi bond and presence of acidic hydrogen. So this is C, triple bond C, this is H, let's say this is R. So now in this case, this particular hydrogen becomes acidic hydrogen because this is Sp, this is Sp, and the electron negativity of Sp is very high as compared to Sp2 and Sp3, right? That is the reason this sp is going to have shared pair of electrons towards itself and making this hydrogen think that why I am even here, what is my need. If you just want to take the electrons with yourself only, then I'll just go and I'll just chill with someone else, right? So this is the same case if you and your friends are, let's say, eating something like pizza, right? And they keep all the slices, they are eating all the slices, they are not giving you anything. You will say, I don't want them, I'm just going, right? So same cases with this hydrogen. So hydrogen is very acidic in nature. Hydrogen wants to go, right? That means hydrogen can easily be released here. That's why alkynes are very acidic in nature. Right? Okay. So now because of the acidic nature of alkynes, there are some reactions that are shown by alkynes. Same reactions that it will show, same reaction that the acid will show are shown by alkynes. For example, we know that when an acid reacts with metal, right, it will give rise to salt plus hydrogen gas, right? Similarly here, this is an acidic in nature. So this hydrogen will be replaced by the sodium here and you will have the formation of a salt and hydrogen gas here, which confirms that hydrogen is very acidic in nature, right? Now let's talk about the next thing, guys, here let's talk about NaNO3, what happens? Wait a minute. Yes, with NaNO3 also same thing will happen. So here with Na, this will be replaced and you will have the formation of salt plus H2 gas, right? Again, this is showing you the acidic nature of the alkyne, right? Then next is this reaction utilized for the preparation of higher alkenes. Right now, this is the reaction that we utilize. This is how we can convert our lower alkyne to higher alkyne, and this is one of the important reactions, right? That's what I am telling you. These reactions are repeated in your exam. They are not asked as it is, right? There will be some chain reactions in which A to B, B to C, C to D, they will mix alcohol phenols, hydrocarbons, haloalkanes, halorenes together, right? And they will ask you a question out of that. So in those kind of questions, these things are asked, right? They will start from alkyne. Firstly, do you remember the preparation of alkyne? From calcium carbide, from magnesium carbide. They will start the reaction from calcium carbide, right? Then from that they will show you some reaction like this. Then you will increase the alkyne chain. Then there are other reactions of alkyne also that they can show you, right? So this is how chain reactions they can ask you in the exam, right? So every single reaction that you see here is important, right? Especially the one that I'm marking important, right? So now here NH3, this H will be replaced by, wait a minute, this will be, wait a minute, this will not be NH3 here, my bad, let me just correct it. This will be NaOH. Right? Let's say anything you have NaOH, you have, let's say, sodium here, simple sodium you have, right? Metal you have here, let us sodium, right? Now what will happen, this hydrogen will be replaced by the sodium and you will have the formation of H2 gas here, right? Now this particular thing that is negative and positive here, when you react this with Rx, right, what will happen? NaX, this is also positive, this is negative. This R will be replaced by the sodium here. You will have the formation of RCC, let's say this is R dash, right? RCC, R dash, and here NaX will be eliminated, and that's how you can form propyne from ethyne. You can form butane from ethyne. Right? You can increase the number of carbons in the alkyne from this particular reaction. This is what makes this reaction so important, right? Okay. Now, because of the acidic nature, triply bonded carbons are acidic, but not all the hydrogen atoms of alkynes, right? Only triply bonded, that means if you have C triple bond, let's say C triple bond C, this is C, C. Now this is H2, this is H3. Now here in this case, if you have something like this, it has no acidic hydrogen here, because to the triply bonded carbon there is no hydrogen attached. And these hydrogens, if you talk about these hydrogens, these hydrogens, these hydrogens, these hydrogens, they are not acidic in nature. These hydrogens are not acidic. Only those hydrogens which are connected to the triple bond are acidic in nature, right? Next is the hybridization is sp. sp hybridization has this character, more is the electronegativity, this I have already taught you. Carbon of triple bond is more electronegative, so it can stabilize negative charge better than other carbons. That is the reason here this H positive will be eliminated, right? Because this negative charge it can hold, because this is a sp hybridized, it can hold that negative charge so easily. That's why this is acidic in nature. Yes, everybody? Clear? Oh, yes. Now, let's talk about the reactions, the type of reactions that are shown by alkynes. The only hydrogen which is attached to sp carbon, that is acidic. Yes, definitely you are right. Acid base gives salt, water. Yes, definitely Zoro. Correct, correct, correct. Very good. There were some technical issues, what to do, right? It was not in my hands only, right? That's why I just, that session got ended on its own, right? Something weird was happening to my studio, right? So it was like if some ghost is, you know, itself, it was getting hanged and sometimes getting on and off on itself only. So I was like, what is happening, right? So that's why. Right? Okay, so let's do chemical reactions, chemical properties of alkynes. Everybody, let's do chemical properties of alkynes. First is electrophilic addition reaction. What are electrophilic addition reaction? What type of electrophilic addition reaction? That means pi bond will break, positive and negative will be attached here, right? Now in all these reactions, one by one we'll see the type of electrophilic addition reaction here. Guys, let me just wear my specs here. I forgot to wear it, but now I am having strain in my eyes. Actually, frankly, I was trying to look stylish, but what to do? My eyes don't make me, like, you know, let me look stylish only. What to do? Okay, so addition of hydrogen here. See, when hydrogen is added in both the parts, hydrogen and hydrogen will be connected when you break one pi bond. When you break another pi bond, again HH will be linked here, connected here, and from alkyne you can have the formation of alkene, right? Similarly here, two pi bonds will break and you will have the addition of two hydrogen on both the carbons, and hence you will have the formation of propane here. You will have the formation of propane here. Got it? You will have the formation of propane here, right? Simple catalytic hydrogenation we are doing, right? This is simple catalytic hydrogenation. Catalytic hydrogenation. Now, do you remember any method where we have converted alkyne to just alkenes? Any method? Yes, we have done two methods of converting alkyne not to alkanes but just to alkenes, where we are stopping this reaction till alkene, and there are two methods here. That is, first is by using Lindlar's catalyst, that is in hydrogenation you are using a poison here. You are using a poison here, right? You are using a poison here to stop the reaction beyond alkenes, and here you will have the formation of cis alkene always. Always here cis alkene will be formed, right? But when you talk about Birch reduction, this is Birch reduction. Let me just write it here, Birch reduction. Birch reduction I am writing. Yes, Birch reduction. So sorry, yes. Birch reduction. Birch reduction. So in Birch reduction, you have sodium or lithium also they can write here in presence of liquid ammonia, and here you will always have the formation of trans-alkene. Here always you will have the formation of trans-alkene. Always and always trans-alkene will be formed here. Vanakam, vanakam, bacha, vanakam. So here sodium, now why trans-alkene is formed? Why trans-alkene is formed? The reason is that sodium plus liquid ammonia, it will abstract one electron from the sodium, and here you will have one electron, right, from the sodium, right. Now what will happen? This is alkene. That electron will attack on one of the carbons and these electrons will shift here. This will give rise to carbon negative. And here, because of this electron, here you will have one free radical. So in one compound, you can see one electron here, one negative here. When you add a base into it, that is ammonia, this ammonia is going to act as a nucleophile, right? So what will happen, electrophile, this is going to get attached here, right? This is because there is no acidic hydrogens that can be replaced, okay? So this H is going to get attached here, and now here you will have one electron. Now it's not like there is only one sodium and there is only one electron in the solution. So many sodium atoms, so many electrons you have. One more electron will get attached here and you will have negative here, right? So to that position again the hydrogen will be attached on the trans position, and that is how you will have the formation of trans-alkene here. Yes everybody, and that is how you will have the formation of trans-alkene here, right? Okay. Then in the addition of hydrogen, we have Sabatier-Sanderson reaction, again in which we do catalytic hydrogenation in the presence of nickel or Rene nickel. If you take nickel here, the temperature should be very high, like 200 to 300 degrees Celsius. If you take Rene nickel, then the moderate temperature or warm will also work. By warming only, it will get converted to alkane, right? Okay, this also we have done in alkane part, right? Then the next is addition of halogen here. In addition of halogen, what you will have here? Let's say you have addition of halogen here, what will happen? In the addition of halogen, see, we have bromine. That is, what is the color of bromine? That is reddish orange color. Solution of bromine, that is reddish orange in color. If that color decolorizes, that means there is unsaturation present. This also we have done in preparation of alkenes, if you remember, right? Preparation of alkenes. No, I think we have done this in properties of alkene. This same we did in properties of alkene as well. Same reaction will happen here, right? Br to add, anti-addition will take place. Anti means from opposite side Br will attack. One Br will be attached on this side, other will be attached on this side on the opposite positions by breaking the pi bonds. Then if you add one more Br2, again on the opposite position, that means one Br will be attached here, one Br will be attached here, and hence you will have the formation of tetrahalide here, right? In the end you will have the formation of tetrahalide, right everybody? Next is addition of HX. Now alkynes form geminal dihalides with HX because reaction follows Markovnikov first and second rule. Now in HX, do you remember, see, reactions are same as what we did in alkenes, okay? Corresponding to that only we have all the reactions. Just like in the alkenes, you have addition of HX which follows Markovnikov rule. Here also it is going to follow Markovnikov rule, right? So Markovnikov rule means here you have, this can be CH2, CH3, so definitely more hydrogens will be there. Here there will be less, wait a minute. In this case, this is one hydrogen. So I don't know what is this R actually, right? So rather than writing R here, what I'll do here, right? I'll just change it, okay? I'll just change it. Okay, just give me a second. I'll just change it. I'll write something else here. some other alkynes from your example you can understand in more detail, right? So what if you have CH3, C triple bond CH, right? C triple bond CH. Now to this particular carbon you have no hydrogen. Here you have hydrogen and you are adding HX here. So this is H positive, this is X negative. Markovnikov rule says that electron negative element, that means the one that is negative element, that will be on the less number of hydrogens, right? So that means over here. So this is CH3, this is C double bond CH, and here you will have the attachment of X and here you will have the attachment of H, and hence that will be, again we will again apply this rule, that is HX, again we will add, this is positive, this is negative. Again what you will have, this is CH3, this is C, even now less number of hydrogens are here, so this will be CH. Now with the blue pen there was what was already there, and now with the red pen what we are adding now, X and H here. So can you see you have the formation of, what are these? Geminal dihalides. Geminal dihalides. You have the formation of geminal dihalides from the Markovnikov addition. Okay? I think 1.5 are, yes. So here you have the formation of geminal dihalides, right? From directly what I have done is I have just applied Markovnikov addition here, right? Next guys, in the presence of peroxide, in peroxide what we used to do? In peroxide we used to apply anti-Markovnikov addition. Anti-Markovnikov addition. That means in this case negative part will be attached to more number of hydrogens, okay? So here what is the negative part? This is positive, this is negative, this will be attached to this carbon here, and hydrogen will be attached here, and hence you will have the formation of this alkene. Again you will add one more HBr, this is positive, this is negative. Negative part will be attached to more number of, now here the question is, ma'am, this also has one hydrogen, this also has one hydrogen. But initially where you had more number? Here, right? So that is why it will be attached here only, right? So again Br will be attached here, and again you will have the formation of geminal dihalides. Geminal dihalides. Geminal means on the same carbon you are attaching the group here. That is geminal dihalide, okay? Now next is addition of HOX. Do you remember what we did there? We'll do the same thing here. Now in alkynes you will see the application of tautomerism in so many reactions, right? There will be Kurchov's reactions that we'll do. There are so many reactions where you will see that there is the application of tautomerism, right? Let's see how. So this is OH negative, this is X positive here, right? Negative part, it will follow Markovnikov addition. So this is RC double bond, this is CH, right? Negative part is attached to the less number of hydrogens, okay? So less number of hydrogen means this one, negative part is attached here, and this is X. Now, can you see this particular portion is nothing but this is enol? Can you see this is enol? And that is the reason it will get tautomerized. It will get tautomerized. We will tautomerize this, and hence you will have the formation of a new compound here, right? Okay. So in tautomerism, what exactly we do, guys? We mark here 1, 2, 3. The double bond of 2 and 3 will shift here, right? This is RC, this is C, this is H, this is X. So the double bond will shift here, this double bond will shift here, this hydrogen will shift here, right? And this hydrogen will shift here. And that is how, can you see what is a compound? It's not only ketone. On the alpha position you have halogen here. So what you can say, what is the formation here? Alpha halo ketone. It's not only simple ketone that is formed, it's alpha halo ketone is formed here from the reaction of alkyne with HOX. The reaction is quite simple, so don't cram these things, understand these things, that will be better for you, right? Okay, yes everybody, okay, understood? So that is how the reaction will take place. Alpha halo ketone will be formed here. Okay, yes, this we have done already. Now, do you remember there was another reaction that we discussed in alkyne, that was hydroboration reaction. In hydroboration, what we did, see, you had 2 pi bonds there, here you have 3 pi bonds, right? And you have borane and you have BH3, that is diborane you have here, right? So in this case, what will happen, 1 pi bond will break, and here you will have the attachment here. Here what will happen, hydrogen will be attached, and here you will have the attachment with the boron. Now because here 3 hydrogens has to be replaced, so here you will have 3 here, right? And in that case you will have the formation of this kind of compound. Do you understand it, guys? What we do, we break 1 pi bond and 1 valency, and 1 valency here we are left with, right? This valency here we are left with. So this valency with carbon I am stating like this, right? And we replace 3 hydrogens, right? That is why here you will have 3 alkyne groups, alkyne molecules, where the pi bond you will break and 3 hydrogens will be attached. That means 1 hydrogen is attached to each alkyne compound, right? And that's how instead of be hydrogen, this alkyl group altogether will be there. Then this is hydroboration part and this is oxidation part, where what you will have, this particular bond will break and this will be converted, here OH you will attach. This is what we used to do in hydroboration before also, right? But there we had single bond here, and here you will attach OH, so alcohol will be formed, right? But now here you have double bond here, and now you are attaching OH. That is the reason here you will call it enol. Okay, this will be called as enol, right? Because this is en and ol. So again tautomerism will take place. You will mark 1, 2 and 3 here. So double bond here will be changed here. Hydrogen will shift to this position. So you will have CH3, CH2, COH, that is aldehyde will be formed in the case of hydroboration, and ketone will not be formed here, always aldehyde is formed, because always terminal you will have here. Okay, yes, everybody do let me know if that is clear, right? Okay, yes, right everybody, chalo. Now let's talk about the next one, right? That is nucleophilic addition reactions. Now guys, we'll talk about nucleophilic addition reaction. Everybody ready? Ready? Okay. Yes students. Yes students. Now in that, if there is X positive is eliminated and OH is eliminated in that case. Okay, because fluorine is most electronegative, right? We say that fluorine, and HOF does not exist. HOCl will exist, HOBr will exist, HOI will also not exist, right? So they have less electronegativity only. That's why we have X positive. X means chlorine or bromine. We don't mean fluorine, because fluorine is very explosive in nature. Okay, Zoro? Okay. Yes, everybody. Ready for the next part. Nucleophilic addition reaction, because of some technical issue that happened, right? Yes. So alkynes are also miscible and do not react with water. They also don't react with water. However, one molecule of water adds to this on warming with mercuric sulfate. That means with addition of water, you can't just directly, if you remember in alkene how we used to do addition of water, by just adding acid, Do you remember just by adding acid? We don't need any mercuric salt there. Here we need mercuric salt here. Mercuric sulfate is needed, dilute sulfuric acid is needed, and the temperature is very high to form the carbonyl compounds here. Right? So let's talk about this reaction is also called as Kurchov's reaction. The spelling may be wrong, right? So that is also named as Kurchov's reaction. Let's talk about how it is done, right? So here, let's say you have this particular example. Here what you will do, let's talk about that. Here what you will do, let's talk about that, everybody. So here if you see, firstly this is H positive, this is OH negative, right? In this case, OH negative part according to Markovnikov addition. According to Markovnikov addition, what will happen? Negative part will be attached to the less number of hydrogen by breaking the double bond. But both have same hydrogen. Here also one, so it doesn't matter. So you can attach it here, you can attach hydrogen here, and this is going to be the reaction. Now can you see this is enol form, this is enol form, right? Again tautomerize it. So this will be 1, 2, 3. So what will happen? This bond will shift here. Again after tautomerism, guys, tautomerism, this bond is going to shift here, and what you will have here, this is CH, this is double bond O, this is CH3. Because hydrogen is going to shift on the first position, this bond will shift here. So this will become CH3, and here you will have the formation of aldehyde. Now, just now I told you one thing, that is in case of hydroboration reaction, you can not form ketone, not possible. But in this case, you can, right? So let's see how. Let's see how. So you have this particular part, again same thing. Now guys, tell me which will be carbocation. Which, or you can just add Markovnikov rule here. This carbocation will be more stable. So this will be positive. So that's why negative is attached here. Why this carbocation is more stable? Because of this alkyl group. Right? That is the reason we will attach OH here and hydrogen here. Right? And we will break this pi bond here. And we will break this pi bond here. Right? And this pi bond will break here. Right? That is your enol. If you see, this particular form is called the enol form. This particular form is called the enol form. Now, what we will see here, we are going to tautomerize it just like we did in the last case. Tautomerism. Tautomerism. Now in the tautomerism, guys, what you will have, this will be 1, this is 2, and this is 3. Double bond will shift here, hydrogen will shift here. Let's talk about this. This will be CH3, CH2. Here you have CH and here you have 1. So what will happen? Double bond will shift here and hydrogen will shift here, and hence you will have the formation of ketone from the acidic hydration of alkyne in presence of mercuric salt. That is also called as Kurchov's reaction. Okay, everybody, do let me know if that is clear. Butanone is formed actually, butanone, okay, because here double bond is not at the end, so this is ketone, so that is butanone is formed here. Yes, everybody, do let me know if that is clear to all of you or not. Do let me know, guys, if that is clear. Yes, everybody, that is clear. Why the students are not here today? What has happened, huh? That is the basic, huh? In the last lecture, students will, that's why the percentage of toppers are very less, right? Because eventually students are not going to watch the last lecture of any chapter, even though important things are there. right? That is the reason consistency is so important. Only few students, when I start the next class, in the first lecture of any chapter, you will see students there. Firstly, it's like a movie, like they watch these lectures like a movie, like a Netflix movie, that okay, we'll watch first few episodes, last it is becoming boring, ma'am, so we'll not be able to watch it, right? So guys, you need to be very consistent, okay, that you need to take care, right? Now next is addition of HCN. This is H positive, Cn negative, so this will be attached to less number of hydrogens, and in this case both are same, so anywhere it can get attached, so that will give rise to vinyl cyanide, okay, that is called as vinyl cyanide, because on the vinylic position, vinylic means on the double bond carbon, when you have the attachment of Cn, that is called as vinyl cyanide, and this is a very important compound, that is acrylonitrile, from where you have the formation of Orlon, right? This is an important thing. They can ask you, Orlon is formed by polymerization of a compound which is formed by the reaction of alkyne with which thing? Answer will be HCN. HCN, when you react here, you will have the formation of vinyl cyanide, that is acrylonitrile, which is a very important compound, right? Because it leads you to the formation of a polymer, that is Orlon polymer, right? Okay. Yes, everybody. Describe mechanism nucleophilic addition cyanide to an aldehyde. Okay, to an aldehyde, same thing will happen. Yeah, aldehyde too, we are not doing it now. Cyanohydrin you're talking about, I'll talk about aldehyde also. Aise to if I start taking your doubts like that, right, I'll do only other chapters in this chapter, right, because this is slightly out of the topic. We'll do that in aldehyde ketones and carboxylic acid, okay. So wait for that time. Now addition of acetic acid. If you add acetic acid, what will happen? This is negative, this is positive, and here this negative part will be attached to less number of carbons. So this is OCOCH3. That will be formed here, right? Any hydrogen, always remember negative part to less number of hydrogen. Negative part to less number of hydrogen will be added, okay. Here both are same, but let's say you have R here, right, okay. In that case you can say it is added to less number of hydrogen, okay, understood. Next guys, we have complete oxidation reaction, right? This have we discussed about this in this is the third time I'm taking out this particular reaction, right? This is the third time I'm taking out, wait a minute, okay, this is the third time I'm taking out this particular reaction, where CnH2n plus 3n minus 1 by 2 n of CO2 and n minus 1 of H2O will be formed. Similarly, we have a reaction of alkene and alkene as well, that I did in the first lecture of hydrocarbons, right? Then now let's talk about KMnO4 ozonolysis, how these things takes place, right everybody? Let's talk about KMnO4 ozonolysis, how these things, I don't know why the students are not there. Why so less students are there, huh? Wait a minute, let me ask the students why they have not joined the class, right? What is happening? Wait a minute, let me just ask the students to join in. Okay, yes. So now let's talk about oxidation reaction. Let's talk about KMnO4. So in the similar ground we discussed about oxidation of alkene. Now we are going to discuss about oxidation of alkyne, right? So what are the things that we can do here? Dilute cold KMnO4, dicarboxylic acid or vicinal glycols can be formed, break the pi bonds and attach OH on both the carbons, right? That you can do here, break pi bonds and attach OH carbons on both sides. Yes. Two carboxylic acid or ketones can be formed, break the double bond, attach double bond on both carbons and convert hydrogen to OH if possible. Let's talk about one by one. So here I am using dilute cold KMnO4. In dilute cold KMnO4, which thing will take place? Okay, yes, very good, Sumit, Manoj, Zoro, very good. So in dilute cold KMnO4, firstly you will break both the pi bonds, two pi bonds break, and there you will add OH on both the sides. Okay, this is OH here, OH here, OH here, OH here, right? Now we know that OH on one carbon is not at all stable. So this will be eliminated here, hydrogen will be eliminated, and hence you will have the formation of CH3, this is C double bond O, C double bond O, right, and this is CH3, right. So diketones are formed here, right. So what is formed here? Diketones are formed here. When you attach OH here, that is converted to this C double bond O, right. That is formed when you only use dilute cold KMnO4, right. But what if you use hot concentrated KMnO4? Then what will happen? When you use hot concentrated KMnO4, what will happen? For hot concentrated KMnO4, you will have to further break this bond and this will be converted to CH3 C double bond OH. This is CH3 C double bond OH. That is further converted to OH because further oxidation we are doing, right? This is OH and this is OH, right? That is the reason ketones or carboxylic acids are formed when you use hot KMnO4. When you use hot KMnO4, directly this thing is formed in case of hot concentrated KMnO4. But when you have dilute KMnO4, till here you will have double bond O. Again I am repeating, for dilute cold KMnO4, you just have to break two pi bonds and break these bonds, attach double bond O. This one bond will always be there, right? That is your simple dilute KMnO4. But if you have hot KMnO4, further this bond will break and you will attach OH on both sides and that will be your answer. Okay, and that will be your answer here, right everybody? Okay, next is this question here. This we have done. Wait a minute. Next is this one. Now, this also we have done, right? This we have done, that how you will have the formation of this compound here, right? This also we have done. Okay, this also we have done. If you have dilute KMnO4 here, what you will do, this will be CH, this will be converted to double bond O, and this is converted to C double bond OH, right? On further, you will break the sigma bond here and that will be further converted to HC double bond OH, and this is HC double bond OH. That is further H is converted to OH, so that will be C double bond OH, C double bond OH, that is C double bond OH and OH. That is H2CO3 that is further converted to H2O plus CO2. So directly in books you will see that it is written that alkyne will give you H2 and CO2, but how it is going to give you? By this particular reaction. Okay. Now, ozonolysis, which is similar to what we have done now. Ozonolysis is similar here. Okay. Thank you, Sabari, thank you so much. Okay, thank you, Vijay. So, now guys, if you see this here, ozonolysis is same as a KMnO4, right? Now, ozonolysis also takes place. We have two kind of ozonolysis. One is reductive, one is oxidative. Remember, in case of alkene, when you have Me2S, methyl sulfide, it will give you reductive ozonolysis. But here methyl sulfide is going to give you oxidative ozonolysis. That is one of the exceptions, right? Now, ma'am, what will happen? This is same as dilute KMnO4. This is same as hot concentrated KMnO4. Answers will be same as, here the answer will be same as dilute, here the answer will be same as hot concentrated KMnO4. And how the reaction will take place? You will have the formation of ozonide here, right? That will further lead you to the formation of reductive or oxidative product. Let's see how reductive oxidative product will work. Similarly, what you will have if there is oxidation, so this is methyl, this is C double bond O, C double bond O, pi bonds will break, and here also you will have methyl, right? This is the answer for reductive ozonolysis. Reductive, or you can just write reductive ozonolysis. If you further do oxidative ozonolysis, here you will have the, you will break this sigma bond here, and here you will have hydrogen. This will be methyl, you can say this will be C double bond O, this is methyl as it is, this will be hydrogen here, right? That will be placed, this hydrogen here, this hydrogen here, this bond will break here, right? Here these two pi bonds will break, right? And hence this is further converted to, with more oxidation. If you further add oxygen here, with further oxidation, this is converted to C double bond O OH plus C double bond O OH. That means acid will be formed in this case. Okay. Same reaction I have done, that I have done before, right? Okay. Definitely they are more than enough. Megha, more than enough, right? Okay. Another oxidation reaction is where you will have alkyne. You add selenium oxide and this is directly converted to diol, right? This is directly converted to diol. This will be converted to CHO. This will be converted to CHO, a direct reaction that you should remember. Then there is fourth kind of, till now what we have done electrophilic addition, nucleophilic addition. Now we are then we have done oxidation reactions. Now we are doing substitution reactions. Okay, so what will happen in the substitution reaction? Let's talk about that. So substitution reactions are shown by the acidic hydrogen. So when you add NaNH2, so in this case also this hydrogen will be replaced by the sodium here, and hence you will have the formation of the salt. So this acidic hydrogen will always be substituted. For example, you have CuCl3. This hydrogen will be replaced by copper. Here this hydrogen will be replaced by this silver. But these are also used as distinguished test, because in this case when you react alkyne with CuCl3, you have the formation of a salt which is a reddish brown precipitates are formed. See, what is the color of copper? It is reddish brown. So reddish brown precipitate you can remember from there, right? And if this hydrogen is replaced by Ag, you will have the preparation of this silver salt which is white precipitates. Okay, so that is the reason we will study in aldehyde ketones, that alkynes give positive tolerance test. So we can say alkynes give positive tolerance test, but no silver mirror. So how they are giving positive tolerance test? Because with the reaction of AgNO3, they have the formation of white precipitates. That's why we say that they are giving us positive tolerance test, right? Okay. Very good, Sabari. Very good. Awesome. Very happy for you. Chalo. Now let's talk about polymerization reactions. So what is polymerization? Linear polymerization. Linear polymerization is when, for example, you have, this is ethyne. At very high temperature, using catalyst, this is converted to polyethene. Okay? Polyethene. Right? So, linear polymerization you don't have to do for JEE Mains because polymers chapter is already not in your syllabus. But for JEE Advanced, yes, obviously you need to do that because you have a specific chapter for that. But this cyclic polymerization is very important. For JEE Mains also it is very important. Let's talk about that how. So, this theory part you can read yourself. I'll just tell you what exactly will happen. 3 molecules of ethyne, 1 pi bond will shift here, other pi bond will shift here, another pi bond will shift here, and hence you will have the formation of an aromatic compound. That is called as cyclic polymerization, and this reaction is a very important reaction. Directly they will give you RHT, red hot tube, red hot iron, copper, quartz, any of this tube they can use. Octacarbonyl cobalt with bromine can be used to have this particular reaction, but the most famous is if they write RHT, that means they are talking about red hot tube, and in this is actually a very important reaction. Now can you see how they can ask you the question? Let's say from calcium carbide you have the preparation of a compound A, from there you have the formation of compound B. Now they will ask you what is RH, what is this B? From calcium chloride you will think, ma'am, hydrolysis of calcium, you will not even think that you will have formation of benzene here if you have not gone through these reactions, right? So here you will have ethyne. From ethyne you have the formation of, with RHT you have the formation of benzene, and that's how further they can show you so many reactions of benzene. They can convert it to phenol and give you the reactions of phenols. Right? So that's why alkyne is so important for you, right? Because with alkyne you can shift it to aromatic ring, and from that you should know the aromatic reactions which they will further ask. So it's a very important cycle that goes here. That's why this reaction is so important, right? Let's do one question here, guys. Before question, let's do question only. A compound A on reaction with X and Y produces same major product but different A and B. Oxidation of A gives a substance produces by ants. This we have not done, right? So it's quite simple only. So you have a compound A on with X and Y, on reaction with X and Y produces same major product. Major product is same but different product A and B. Okay, got it. So basically what is happening here, one is, let's see the options, Options is KMnO4, H positive dilute KMnO4 dilute, and this is very high temperature. KMnO4, H positive O3. See, either you compare O3 or you compare this. See, definitely what is happening in this case, what is happening here, A is a substance produced by ants. That means A is this thing. Right? So what will happen here? The double bond will break. You will have double bond O here. With further oxidation, nothing can happen here. But with further oxidation, something can happen here. Right? So if you have low oxidation and high oxidation, right? If this is a product of high oxidation, that means here more oxidation is happening. So that is the reason here KMnO4 reductive and this is acidic, okay? Here KMnO4, this is reductive. If this is reductive, yes. Okay? So now this is how we will do this. That here you will break this bond, this is double bond O, this is double bond O. This will remain as it is because whenever you do high oxidation, the hydrogen connected to the carbonyl carbon is changed, right? So low oxidation, high oxidation will give you this product as same that they have given here, right? But this is going to change. What is going to change? This will become HCHO, that is your formaldehyde that is given by ants. And if you have further oxidation here, right, this will be converted to H2CO3, which is going to give you CO2, right? That is the reason here you will have the formation of CO2. That means here you will have high oxidation, that is KMnO4 in presence of H positive, and here you have low oxidation, that means reductive ozonolysis. They can also write here, KMnO4, dilute KMnO4, right? We can also write here O3 H2O2, oxidative. This also we can write. Let me see if there was any option like that. So that means A has to be less oxidation. So this is not less oxidation, this is less oxidation, yes. This is not less oxidation, this is less oxidation, yes. This should be more oxidation. So this is not more oxidation, this is more oxidation. But here the temperature is quite high, na? Here the temperature is temperature is also not high. So this is dilute KMnO4, right? This will also not take place. KMnO4 H positive can take place here, right? So this is also possible. So both should be possible, right? Okay, because then yes, it is again converted to formic acid, that we know, right? So answer will be D, but B also can be the answer because KMnO4 dilute is also going to give you the same product here, right? So this is also not an incorrect one, right? Either they should decrease the temperature, increase the temperature here, right? Something should happen here so that this does not give rise to the same product here, right? Okay, yes everybody, now let's start with the benzene. Ketone won't be changed, yes. Okay, yes everybody. Let's start with benzene compounds here. Aromatic compounds. Let's start with aromatic compounds everybody. Let's start with aromatic compounds, benzene compounds here. Let's talk about this, right? And you know, these are some of the very, very important reactions that you are going to again and again do, but this will form the base of it, right? So first is benzene. You have, it's not like this is the actual structure of benzene, this is the resonance hybrid. In reality, benzene is existing in the, resonance structures it is showing, right? It is shifting here. These are the Kekulé or canonical or resonance structures, and it is going to form this resonance hybrid that we usually use, right? Now it is found to be resonance hybrid of two structures. Aromatic compounds containing benzene ring are known as benzenoids, and the one not containing the benzene ring are non-benzenoids, right? So now let's talk about the nomenclature of benzene. This, guys, we have discussed this. When you have on benzene CH3, that is toluene. If you have C2CH3, that is called ethyl benzene. If you have CH3 on the ortho position, that is orthoxylene. On meta position, you will have metaxylene, or para position, you will have paraxylene. And if you have 3-methyl here on the adjacent position, that will be trimethyl, but this is also a very, very important compound. If you have, this is formed from propyne, RHT of propyne. That means cyclic polymerization of propyne will give you this reaction. It's a very important reaction, okay. So, when you have CH3 on the adjacent position, that is called as mesitylene, which is again a very, very, very important compound, okay, which is again, guys, a very, very important compound, right? Now, let's talk about preparation of benzene, right? So, 3 ways we'll do it. First is cyclic polymerization that we have just discussed, a decarboxylation, then reduction of phenol. Then there are other methods also, but these are some of the main methods. First is, have we discussed this? With ethine in the cyclic polymerization, bonds will shift and hence you will have the formation of benzene, right? Directly with the red hot tube, that is RHT, right? Here you can also write with propyne in RHT, you will have the formation of mesitylene, okay? Then second is decarboxylation reaction. So now if you remember, if you have RCOONA, right? Here you have soda lime decarboxylation Na, and this will give rise to RH. Here this COONA is this thing. Like here COONA is eliminated and here you will have the addition of H here. Similarly here COONA is eliminated and you have the addition of H here, which will lead you to the formation of benzene. So benzene can also be formed from soda lime decarboxylation reaction. I am fine. I don't know why the attendance is so low. Maybe the students will watch it on the recorded version, right? So I seriously don't know, guys, right? Okay, third one is phenol. From the reduction of phenol, that is zinc dust, okay, directly this OH will be reduced to hydrogen and hence you will have the formation of phenol. This is again a very important reaction. This is again, guys, a very, very important reaction. This is also asked so many times, right? Then let's talk about from chlorobenzene. So in chlorobenzene, directly you add catalytic hydrogenation. The Cl will be replaced by hydrogen. You will have the formation of benzene. Or you can have this reacted with magnesium. You will have, this is, let's say, R, this is Cl plus Mg, that will give rise to RMgX, right? That means this particular Grignard reagent will be formed. This is nothing but this is RMgX. That is your Grignard reagent. On hydrolysis, do you remember, guys? We did on hydrolysis how Grignard reagent is like totally crazy for proton donors, and water is a proton donor. So Grignard reagent shows two kind of reactions. One is with proton donors, it is converted to alkane. It will replace this MgX with hydrogen and you will have the formation of RH. So this benzene, here you will have the elimination of MgX and you will have the addition of H here. That will lead you to the formation of benzene. Okay, do you remember that? These are the things, same reactions repeated in different ways, right? So that's why this is actually the first chapter. By the time you reach aldehyde ketones, you will find it easy because reactions you will have the habit of repeating them again and again in other chapters. Now let's see from sulfonic acid. You have SO3H, you add water and HCl, this SO3H will be replaced by hydrogen. Okay, that is again the reduction reaction. Diazonium salt, this you will see in amines as well. This is aniline. This is a condition where aniline is converted to diazonium chloride, which is NaNO2HCl, or you can say HNO2, directly HNO2. Condition is the temperature has to be 0 to 5 degrees Celsius, and this will be converted to diazonium salt. Diazonium, which is a very important salt. Very important salt, guys, diazonium salt. We will see in amines chapter, that is the last chapter of organic chemistry before biomolecules, of course, right? You will see so many reactions of diazonium salt, and this is one of the reactions where diazonium salt in the presence of H2, H3PO3, and here you can also use ethanol. You can also use ethanol here. It is converted to benzene directly. Okay? These reactions, more you do these reactions, more they will be on your tips, right? They are very important reactions. You just have to revise them again and again and again and again, right? Okay, guys, tell me, any problem in the preparation of the benzene? Any problem in the preparation of benzene, guys? Any problem? Yes, everybody. Okay. Now let's talk about, let's talk about physical properties of benzene, right? Aromatic hydrocarbons are non-polar molecules, right? Polarity here, aromatic hydrocarbons are non-polar, right? The polarity is not there, it is 0, right? Mu is 0, are usually colorless liquids and solids with a characteristic aroma. That's why it is aromatic. They have a characteristic aroma, right? Naphthalene balls, which are used in toilets. So you must have seen naphthalene balls that we used in toilets also, that we used when we pack our bags for months and months. We don't want any insects, mosquitoes, right, to destroy our clothes, right? So that's why we use naphthalene balls, right? So these are for the preservation of clothes, because unique smell of the compound and the moth repellent property, right? Because of its unique smell, it can attract the moths, the insects, and because of its moth repellent property, we use it. Then aromatic hydrocarbons are immiscible with water, but are readily miscible with organic solvent. They don't show, because see, benzene is non-polar, mu is 0 in this case. So with polar molecule like water, it will not get dissolved. A non-polar molecule will need a non-polar molecule. That's why they are easily dissolved in organic solvents. They burn with a sooty flame. Why sooty flame? Because at the end their hydrogen and carbon is there. So that is why they burn with a sooty flame, right? Now guys, let's talk about the chemical properties of benzene, right? Okay. In the end, I think in next 10 to 15 minutes, we'll start doing the PYQs, right? So chemical properties of benzene. Arenes are characteristic. Arene means aromatic benzene only. Arenes are characterized by electrophilic substitution reaction. They are the most famous reaction of aromatic compounds that you will see in every other chapter. You will see these. In phenols you will see, in anilines you will see, in benzoic acid, benzaldehyde, right? All these you will see these electrophilic substitution reaction, okay? Under special conditions, they can also undergo addition and oxidation reaction, but they are very specific, right? So firstly, let's talk about electrophilic substitution reaction. So that means an electrophile is going to attack on any of the position, and here hydrogen will leave and you will have the formation of compound, right? So let's talk about how this actually happens, okay? So just see the simple mechanism here. What exactly happens? Here you have pi electron cloud that is revolving in the benzene ring. This is electrophile, which is electron loving. It wants to go where it sees the electrons. So this will be attracted here. That means here what will happen? Firstly, this bond will shift here because they want to make a location, a empty space for this electrophile to attack, right? So that what will happen when this will go, then here the electrophile is going to attack, but usually we draw the arrow by this side. Usually the arrow in the organic chemistry reactions are for more electrons to less electrons. So here you have more electrons, so it will be like this, right? Usually we draw it like this, but actually it's like this, right? So this particular position will be attacked by the electrophile, and we know that every benzene carbon you have a hydrogen, so hydrogen will also be there, right? Because of that reason here, this pi bond will not be there because this pi bond has already shifted, right? This pi bond has already been shifted here. So basically what has happened here, this was benzene, this pi bond has already shifted, this was negative, this was positive, to this negative electrophile has attached, okay? This is how you have the formation of this erinium ion, right? That is aromatic carbocation. Now you will see resonance here, this pi bond will shift here, you will have positive here, this pi bond will shift here, you will have positive here, right? That means it is going to give you a resonance hybrid that where positive charge is shifting here, here and here, right? And electrons are shifting on the ortho and para, positive charge is shifting on the ortho and para position, and double bond is also revolving here, right? Now again what will happen after this what will happen? In any, you can take any of the resonating structures, what will happen? Let's talk about this resonating structure only. This hydrogen will also leave, the double bond will shift here, and hence you will have the formation of electrophile substituted benzene, right? Okay. Now one by one we'll talk about halogenation, sulfonation, all these reactions which are repeated again and again, right? So in the halogenation reaction, what is the reagent? Firstly, just focus on the reagent, okay? The product is not difficult here, reagents are important, okay? So here you will have cold dark FeCl3 and Cl2. FeCl3 is a Lewis acid. It's a Lewis acid. Because it's a Lewis acid, what it will do? It will, from this Cl, it will take out Cl negative from here and it will leave Cl positive, and here Cl negative will be attached and this will become FeCl4 negative. Because Lewis acid is electron deficient, it would want someone to attack on it. That's why it is pulling Cl negative here, and hence here you will have the formation of Cl positive, which is your electrophile. The Cl positive is your electrophile, which will be replaced on the, which will attack on the carbon here, right? Then in case of nitration, guys, you have HNO3 and H2SO4, right? Where HNO3 is acting as a base, because if you talk about the basic nature or acidic nature of acid is more, right? We know that acidic nature of acid is more. That is the reason in comparison this is less acidic. That is why when you combine these two, this is going to lose H positive, this is going to gain H positive, because this is acting like a base here, right? Now let's talk about how it is done. This is going to gain H positive, and here H positive it will gain, and this will become positive, right? This will become positive, and here you will have the formation of this compound. Now we know that oxygen can never hold a positive charge, so this electron will shift here, and here you will have the formation of NO2 positive, and this bond will break, these electrons will shift here, you will have the elimination of water, and you will have the formation of NO2 positive electrophile here, right? You will have the formation of NO2 positive electrophile here. Tell me, this is the electrophile that is generated, that is going to get attached to the benzene ring. Yes, everybody, clear, right? Okay, and this mixture is called as nitrating mixture. This particular mechanism is same that we did before. There I wrote E positive, here we are writing NO2 positive, which is called nitronium ion, right? Everything else is same, that firstly it will attack, then resonance will take place, then hydrogen will leave from this side, these bonds will jump here, everything is same. That's why I told you the basic mechanism in the starting, right? You just need to replace electrophile, like in halogenation you need to replace this NO2 with Cl positive, X positive. Here you need to replace it with NO2 positive, right? Basic mechanism I have told you. Now let's talk about this particular question, that is benzene or nitration. Yes, everybody. Beta, what do you want me to do? Run marathon here? Like literally run marathon. Benzene or nitration give nitrobenzene in presence of HNO3 in this mixture, where both are acting as base. This is acting as an acid, this as base. Both are acting as acids. This is acting as base and this as an acid. So answer is yes, D is the correct answer. This is acting as a base, this is acting as an acid. This is 2021 question from a very simple statement, right? Next is sulfonation reaction. Let's talk about sulfonation reaction. Now here hydrogen will be replaced by an atom given by sulfonic acid group in the ring, that is called as sulfonation. Let's talk about how it is done. So this is basically oleum or sulfonic acid, or you can have sulfuric acid in presence of SO3. Right, let's see what it is going to give you. Oleum is going to give you SO3, this is the electrophile. Now this is a neutral electrophile if you see. Right, this is a neutral electrophile. Right, this is your neutral electrophile. Now, ma'am, if this is the electrophile, then how come we have SO3H here? Because of internal transfer of hydrogen. Let's talk about that, how internal transfer occurs, right? So from sulfuric acid or oleum, this is going to produce you SO3, right? Once you have sulfur dioxide and sulfuric acid act as sulfonation agent, that is electrophile, this is going to attack here, this electrons is going to attack here. Once they attack here, you will have SO3 negative, because one extra bond it has formed, so SO3 negative it will be. Now guys, this hydrogen is internally shifted here. Let's talk about this. This is the resonance, how resonance works. This bond will shift here, right? This bond will firstly shift here, you will have positive here, then this bond will shift here, you will have positive here. Now, this hydrogen, instead of leaving, it will transfer internally. This hydrogen is internally transferred here, this bond will shift here, and hence you will have the formation of SO3H. This is an important point, that electrophile here is SO3, but because of internal transfer of hydrogen, here you have the placement of SO3H. That is a very important point. Okay, right? Next is Friedel-Crafts reactions. Next is Friedel-Crafts reaction. What we have here, So Friedel-Crafts introduction of alkyl or acyl group. What is alkyl group? You will have R positive as the electrophile, or you will have RC double bond O positive as the electrophile. This will be there in alkylation, right? This will be there in acylation, right? Now how they are formed? You need a catalyst, which is a Lewis acid, right? Or protonating agents like HF, H2SO4, H3PO4, all these things will give you Friedel-Crafts reaction. Okay, so catalyst you should know, either it should be Lewis acid or it should be protonating agent which can give you proton. Either protonating agent or Lewis acid should be there, right? This is very important. Students, just remember that, ma'am, AlCl3, AlCl3. Any Lewis acid will work here. FeCl3, yes. SbCl3, yes. Any Lewis acid which is electron deficient. Any agent which is protonating, which is giving you proton. This is giving you proton, this is giving you proton, this is giving you proton. That means basically an acid which gives you proton. That can also work here, right? So in case of alkylation, you will have the formation of this R positive electrophile that will attack here. Just like here you have the formation of CH3 positive electrophile that has attacked here. But the question is, ma'am, how these electrophiles are formed? So basically you have a Lewis acid. What will happen? In the Lewis acid, it will, this is negative, this is positive. It will take out the anion part from here, right? So here you will have the elimination of R positive, right? But ma'am, what about a protonating agent? Guys, if you have, let's say, RCl and you have a protonating agent, let's say HF, right? This HF is going to give you proton. It will give you H positive. This H positive will get attached to the Cl negative and hence you will have the formation of R positive. So anything will work. You have a protonating agent, you have a Lewis acid, this will work the same way. All you need a alkyl carbocation, right? Okay, this is again the same thing. Instead of Cl positive, now you have this R positive as the electrophile, right? And that's how you will have the reaction. Now, because here you have the formation of a carbocation, so rearrangement will definitely take place here, right? So we know that this will form a carbocation, that is CH3, CH2, CH2 positive, because this Cl negative will leave from this side, right? And this is going to give rise to, this particular thing is going to give rise to this plus AlCl4 negative, right? Here rearrangement will take place, hydride shift will happen. So this will be CH, this will be CH3, this is positive, right? And now here, when this will attack here on the benzene ring, it will give rise to CH, CH3, and this is a very important compound. This has a very important name, very important compound. Can anyone of you tell me? Right? Okay. Thank you, bacha. Thank you. Can you tell me what is this? Can you tell me what is this? This is isopropyl cation, right? It, when attacks from its carbocationic position, it is going to give rise to a compound called cumene, which is a very, 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 very important compound for you. It's very important. They can ask you this in cumene process for the preparation of phenols, right? In the preparation of phenols, we will use, this will be the one of the steps of that preparation, right? That is isopropyl benzene is called as cumene, right? So this is a very, very important compound. Now guys, you can see this is ROH and this is H2SO4. So we know that OH negative will be eliminated here because this is an acid. It will take out OH negative from this side and hence you will have the attachment of R here. From this case, R positive will be eliminated, right? Okay. Because guys, you will say, ma'am, but this is an acid, it should lose proton. Which are, when you compare all of these both, this will act as an acid, this will act as a base. So it will eliminate OH negative. What a work does, what a base does. It eliminates OH negative and hence R positive will be formed. Now let's talk about acylation. In acylation, you have acyl chloride and AlCl3. Again, this is Cl negative. Again, this Cl negative will be taken out by the Lewis acid. This is the Lewis acid, right? And here you will have AlCl4, and this is your acyl cation, acylium ion, which is acting as an electrophile. That will attack here and you will have COR here, right? This can lead you to the formation of acetophenone. Like if you have R as CH3, that will lead you to the formation of acetophenone. Now, it's not like only acyl chloride can give you this answer. Even if you have acid anhydride, same reaction will take place. This negative part will shift here, right? And you will have the formation of CH3C double bond O positive, which will attack on this benzene ring and it will give rise to a compound that is COR. Or if here you have CH3, acetophenone will be formed. Okay, everybody, acetophenone is formed here, right? Yes, you are absolutely right, Manoj. Yes, in cumene process you have phenol and acetone. Yes. Now you have some limitations of Friedel-Crafts reaction. Let's talk about those limitations. Aryl and vinylic halide. That means whenever you feel to break the bond of CCl is tough, then this reaction will not take place, right? So in arylic, what you have? In vinylic, what you have? Wait a minute. This is vinylic. This is arylic. Okay, wait a minute. Now, in the vinylic, we know that these are lone pairs. Here also these are lone pairs, because of which resonance will take place. Here also resonance will take place. Both of them will have partial double bond. Partial double bond. Partial double bond. That means in CX, what you will have here? You will have a partial double bond here. That is why it's very difficult to break this bond. That is why you will not have aryl or vinylic halides cannot be used in Friedel-Crafts reactions. It's a very, very important point, right? Then in substituted benzene, if you have any gives poor yield when electron withdrawing, that means if deactivating groups are attached to it, it will give a very, very, very poor answer. That means yield will be very poor if you have electron withdrawing substituents here, right? Because electron withdrawing, why electrophilic substitution is happening? See, why you go to any shop to purchase when you see good products there? When you don't see good products, you will not shop there, right? So similarly, when the electrophile sees that, oh my god, so many electrons, I am so happy, it will attack. But if there is some electron withdrawing group that is taking out those electrons from the benzene ring, then the electron will be like, no electrons here, why will I attack here? So the yield, the power of electrophile to attack on that particular benzene will decrease if there is a deactivating group attached to it, right? Then in case of anilines, do not show this reaction as this aniline is a base, and in Friedel-Crafts reactions you use Lewis acid. So what will happen? Wait a minute. So what will happen here, instead of this, what will happen? Acid base reaction will start taking place, and here you will have attachment of AlCl3 and a salt will be formed. A salt will be formed here. Acid base reaction will take place because it's a base, this is a Lewis acid, and hence for aniline it is not possible, right? Acid base reaction will take place here, right? Okay, yes everybody in the chat box. Yes everybody, tell me. Now let's start with the hello. Now guys, let's start with addition reactions. So addition reactions are not so easy. Why? Because this is a delocalized pi bonds, right? So it's very difficult to break this, right? Very difficult to break the bonds of benzene. Partial double bond, single bond is there, right? So that is why it's very difficult to break it. So addition reactions are very difficult, but still if you give hydrogen at a very high temperature, that is 150 degrees Celsius, then this will be converted to cyclohexane. It's not an easy reaction, it's a very difficult reaction. Okay, it's a very difficult reaction. Now two reactions that are very famous, that when you give Cl2 in the presence of UV light, that is Hμ, all the double bonds are going to break, and everywhere you will have the attachment of Cl, right? All the double bonds will break, and attachment of Cl. So you can write double bonds break, Cl attached everywhere. This is what happens when you have Cl2Hμ in the presence of light you give it. But if this reaction is happening in presence of Cl2, that too in excess, but in case of anhydrous AlCl3 in dark, then these double bonds will not break. Only Cl will be attached here. This is another reaction. Usually this and this reaction looks similar, but in case of Hμ, double bond will also break, but in case of anhydrous AlCl3, double bonds will not break, right? And this reaction where double bonds are also breaking, that is called as gamma Z. This is also important, right? This also they have asked you, I think this year only they have asked you this question. Okay? Beta, I'll die of heart attack if you ask me what is delocalization, right? Go and watch resonance firstly. Birch reduction. Do you remember we have done Birch reduction before also? We did Birch reduction where what we did, that here you will have benzene, we did that, okay, you will have alkyne that is converted to cis and trans alkene. But Birch reduction in case of benzene is, or in case of aromatic compound is, you have a compound benzene, two double bonds you will have in the end which are opposite to each other. One double bond will break. One double bond will break, okay, and rest of the two double bonds will be opposite to each other. You can also draw it like this, you can also draw it like this, or you can also draw it like this, okay, or you can also draw it like this. It's just that they have to be opposite to each other. They have to be opposite to each other, right? That is the condition. Now ma'am, that was about benzene. But ma'am, if we have any electron donating or any electron withdrawing group attached to it, right? Yes everybody, here it has electron donating, this is electron withdrawing. So if you have electron donating, now tell me guys, if someone donates you something, someone gives you something, right? Someone is helping you, you would want to stay close to them or away from them? You would want to stay close to them. So similarly, here double bond, close next to this will stay, and opposite to that you should have a double bond. That means this compound will be formed, right? Now, if you have electron withdrawing group, someone who is taking away all the money from you, you would want to stay away from them. So, one bond, after one bond, you will have this bond, and opposite this bond will stay. Because if you choose this bond, then this bond will stay and it is closer. If you choose this bond, then this bond will stay, it is closer. So only we want to have bonds which are away. That means these two bonds will stay. So you will have this as the final answer here. Okay, do let me know. But I'll ask the team what is the issue, okay? Okay, yes. Tell me guys, is that clear? Is that clear? Now let's talk about oxidation. Now it's a side chain reaction. Any alkyl chain except 3 degree alkyl. It should not be a tertiary alkyl. Any alkyl chain except for 3 degree alkyl will be converted to COH. And in the end, you will always have the formation of benzoic acid here. Any alkyl chain except for 3 degree alkyl. Tertiary alkyl should not be there, right? Okay. That's why we are saying carbon attached to the benzene must have alpha hydrogen. R can be alkyl, alkenyl, alkylenyl, acyl, anything can be there, but it should not be tertiary. Okay, this also can take place, right? Okay. Next guys, combustion reaction or combustion we have done. These aromatic compounds after combustion will give you carbon dioxide and water. Just like combustion reaction, simply how this happens, right? Now the last part guys is nucleophilic addition reaction, nucleophilic aromatic substitution reaction. Let's talk about this. Let's talk about this. Let's see. First category is addition elimination, then the second category is elimination addition. So addition, firstly adding, then eliminating, occurs when strong electron withdrawing group is attached to benzene. And elimination, that means a formation of benzene at high temperature and pressure, just like Dow's process that we will discuss in phenols. Alcohol phenols will discuss. This is one of the preparation process of phenols that also will discuss. So we are saying that addition elimination, that means firstly you add something, then it is eliminated. This will happen when strong electron withdrawing group is attached. And elimination, firstly you eliminate something, and benzene means what is benzene? What is benzene? This intermediate is benzene. It is formed when first case is elimination, then you add something, right? This we will discuss in phenols, right? So both the reactions are possible, right? All you need to know is when you have a strong withdrawing group and donating group. Now guys, all these things we have already discussed. You can just go through this. I have discussed this in resonance, where you will have activating, which is deactivating, right? This all I have already discussed, right? What is orthopara? I'll just directly show you. When to a benzene ring you have a group which has lone pairs, then it will be plus M, it will show you plus M effect. That means it will be orthopara directors. When on the benzene ring you have a group that is attached to an electronegative, X is more electronegative as compared to G, then this will show you minus M effect, that will be meta directing. Okay. If you are getting confused on this part, then go and watch resonance, right? Because resonance is where I have taught you all these things, ortho para directing, right? Theory part I have just given you here so that you understand what is happening here, right? And here just remember that halogen is different. Why it is different, what happens, all of that I have told you there. This is what resonance lecture I took for 2 and 2.5 hours, that's why I took it there, right? So halogen is ortho para directing but deactivating. This is the exception that I told you, right? Why? Because in halogen, plus M effect is not dominating, minus I effect is dominating. In other cases, mesomeric is always dominating, that's why you have this exception, right? Okay, this all we have already studied in resonance, right? Why it is so, this also we have studied, guys, this also we have studied. So now let's do the questions here of JEE. Let's do some questions, right? Okay. Alkynyl, yes, yes, it can be converted, but you should have, like, if you have a benzene ring, right, if this is C, then it should be hydrogen here, then it can have double bond over here, then it will be directly converted. Then this carbon should be sp3 and it should have one alpha hydrogen, okay, and it should not be tertiary. Okay, yes everybody. Chalo, let's do some questions here. So JEE 2016 question is, consider the reaction sequence below. This is a question. Succinic anhydride AlCl3, then Clemenzin reduction, what exactly happens? For that, some students are thinking, ma'am, what is succinic? And this is one of the most repeated questions and I have seen this so many times. So let's see how this happens. This is called as succinic anhydride, which is very important, right? How can you see this is anhydride and how anhydride takes place? Anhydride is when one oxygen here, right, what will happen? A bond will be shifted to the oxygen and hence you will have, let's say this is double bond O, this is carbon positive, then there will be one carbon, this is one carbon, then there will be another carbon C double bond O, this will be O negative, right? Okay. Now, here it's not like this will, this closed chain has converted to open chain. Some students, they directly attach COCH3 here. No, this is not, it has just this bond we have break. Only this bond, right? Other things are as it is only. So this is CO, CO, CH2, CH2, CO, CO negative, right? This negative will be as it is attached here. You can also put here negative. If you want to be clear that what ma'am exactly is happening, you can have a negative here. So this will be CO from this electrophilic position. CO, CC, CC, CO negative, that will be there. And to this negative, right, you will have H positive addition here, right? Okay. Now, this was the first part, that is Friedel-Crafts acetylation. Next is Clemenzin reduction. In Clemenzin reduction, C double bond O is converted to CH2. So this bond here is converted to CH2. This bond is converted to CH2. And Clemenzin reduction is sensitive to acidic groups. Because here you have acidic conditions. If you remember Clemenzin reduction, that is very sensitive to acidic groups here, right? It is very sensitive to acidic groups, so that is the reason from here hydrogen and from here COH, this whole will be attached and here you will have the formation of a ring. Because this particular COH, right, this is sensitive to acidic condition, right? Because of Clemenzin reduction, this further will be reduced to CH2 and this will be connected here, and hence you will have the formation of this cyclic ring here. From this you have the formation of this ring. Okay, got it guys? And hence the answer will be D is the correct answer. Right everybody? And hence the answer will be D is the correct answer here. Right? Next question is the correct order of, this is 2021, the correct order of following compounds showing increasing tendency towards nucleophilic substitution reaction. Nucleophilic substitution means we need to have electron deficiency here. The one which is most electron deficient will have maximum tendency. So here you have 3 electron withdrawing group. Least, it will have least electron deficiency, it is withdrawing the group, so least electron deficiency, and we need electron deficiency only, right? So that means 4th will have maximum affinity towards nucleophilic addition reaction because least electron deficiency. Then here you have even less than that, here you have even less than that. The deficiency here is more, here it is even more, here it is maximum. Here you have no, see, more is the electron withdrawing. Simple thing is, nucleophilic addition will be directly proportional to electron deficiency. That is directly proportional to electron withdrawing group. So it has maximum number of electron withdrawing groups. So here it will have the maximum affinity towards nucleophilic addition reaction. So answer will be okay, yes, 4, 3, 2, 1. So answer will be D is the correct answer. Okay. Next question guys, we have the correct order sequence of reagents used in preparation of 4-bromo-2-nitroethyl, 4-bromo-2-nitroethyl benzene from benzene, right? So this is a sequence for these. Now do the organic chemistry. Now we have completed one chapter of hydrocarbons. Now after this start doing conversions from organic chemistry NCERT. At least do it tomorrow. You don't have class of chemistry, right? So do it tomorrow. Do it. Please do it, right? Organic chemistry conversion, it will help you to do these kind of questions. And this is what they are asking you, right? 4-bromo-2-nitroethyl benzene is what you have to make, right? That means this is the compound that they are asking you, right? 4-bromo-2-nitroethyl. Okay. So firstly on benzene, now here very important thing is you should know which is meta-directing, which is para-directing. Here GOC plays a very important role. I will tell you how. Firstly, we make COCH3 here directly. Now we know that COCH3, right? This is actually meta-directing. This is meta-directing, right? Then you do Clemenzin reduction here, Clemenzin reduction. Ma'am, then you are asking, ma'am, but can't we just directly do Friedel-Crafts alkylation? Is it in the option? There is no option of Friedel-Crafts alkylation. Only option is Friedel-Crafts acylation. It's not like from this to this you can only do it by Friedel-Crafts acylation then Clemenzin. No. You can directly do Friedel-Crafts alkylation here, but that option is not given to us. So we'll do firstly acylation, then Clemenzin reduction. Then they can also give you here Wolff-Kishner reduction. That will also give the same answer, right? So you need to know this. After that, I know that this particular compound, this was meta-directing, but here this is para-directing, ortho-para-directing, right? Alkyl group is ortho-para-directing, para being the major product. So here para is formed. Now this is ortho-para-directing, this is ortho-para-directing, right? And this is a stronger group. Halogen has more ortho-para-directing effect as compared to alkyl, because in case of alkyl you don't have mesomeric effect. In case of halogen, you have mesomeric effect, so it is a stronger ortho-para directing group, right? So that is the reason here on the para position you will have the formation of NO2 by adding nitrating mixture, and hence the sequence is going to be firstly acylation, then clemenzine, then bromination, then you will have nitration. So answer is P is the correct answer here. Okay, ortho-para directing, EW meta directing. Yes, yes, absolutely correct. Absolutely correct, right? Then next question is, you have again 2021, that is, from the following sequence of reaction the correct products are. The correct products are, this is benzene. Firstly, bromine will be added on any position, right? Then Mg will be added, that means this will become MgBr. Then CH3OH, when Grignard reagent is reacted with CH3OH, which is proton donor? This is proton donor. This is proton donor, right? So here what you will have, this will be converted to benzene. This will be directly, this MgBr will be converted to here hydrogen, that is benzene, and to this Mg you will have the attachment of OCH3. So OCH3 here, so answer will be D is the correct answer here. Okay, how it is done? Firstly bromination, then Grignard reagent. Grignard reagent, whenever it finds any proton source, it will give the proton, replace MgBr with hydrogen, and you will have the formation of benzene. Okay everybody? Yes. No. This is, no, there is no hydrogen bonding. No hydrogen bonding beta here. Hydrogen bonding will be done if this hydrogen is also attached to any electron withdrawing. This is purely based on ortho-para positions, right? Because of bromine is more ortho-para. That is why it is para, wait a minute. Acha, this is not on the ortho position, na? No, my bad. No. This is on the ortho position of this alkyl group actually, right? Alkyl group actually, right? This is on the ortho position of this alkyl group, not here, so it is meta. Yes, it is not on the ortho position of bromine, but it is on the ortho position of this alkyl group. Okay, it is not because of, there is no hydrogen bonding here, right? There is no hydrogen bonding there, right? And hence the answer is going to be D is the correct answer here, right? And now is the time for your homework. Everybody just take the screenshot of this homework and write it down in the comment section. I'll see that how many of you comment down your homework here, right? And before going guys, our test series is right now at a discounted price, that is 999, where you will get part syllabus, full syllabus and topic wise test as well. So if you're looking for good practice questions test series, then go for this test series, which is right now at a discounted price, and it can, the price can shoot up anytime soon. So everybody, link is in the description. Hurry up and click on that button, right? Now I'll be waiting for your comment section, right? I'll see that how many of you do your homework, right? So till then guys, bye bye, take care, and don't forget to like the session, share this with your friends, and in the next class we are going to start with haloalkanes and haloarenes. See you all in the next class. Bye bye.